other part of the analysis, second of the videos. If you haven't seen the first one, I mean, you can do this one on its own, but I reckon you should go back and do the percentage by mass analysis video and the questions first. But on the other hand, you might be okay with that. You just want to go wading straight in with this. Just to remind you, empirical formula, ratio. 4 examples there. A lot of this comes out of organic, that's quite common. So 3 organics at the top there. Ethene, C2H4, not its empirical formula because the 2 and the 4 both divide by 2. So the empirical formula is CH2. Butane, C4H10, both of those numbers divide by 2. C2H5, which reminds you, of course, that, well, reminds me maybe, that empirical formula couldn't exist as that and a compound, because empirical formula and molecular formula or compound formula are not necessarily the same, but sometimes they are, but not necessarily. Now, different sort of thing here. This is one of the propanols, doesn't matter which one. And here, hydrogen, because of the way you write the formula, is in 2 places. So firstly, you need to go C3, combine all the hydrogens, so that's C3H8O. So that's a 1 on the end there. You can't divide that. As soon as you get a 1, nothing's going to go any lower. So the empirical formula is C3H8O. You can't make that any smaller. The 1 would not be there. Now this, not an A-level compound, I have to say, very much a university style compound, but it just serves an interesting thing about how you write an empirical formula. So also it's an opportunity to get one of the lesser known elements in, rhenium. There you go. Don't go that far down the periodic table at A-level normally. So the first thing you would look at with that is go, hang on, let's get rid of the brackets and find and write out how many things we've got. So that expands this RE, and there are 2 rheniums and 10 carbons, 10 oxygens. Interesting compound. It uses carbon monoxide. That's carbon monoxide. Kind of, we can mention that in year 13 if you've got a teacher who's happy with that, like me. And that then, 10 and 2 both divide by 2, so the empirical formula would therefore be ReC5O5. In terms of its structure, very interesting looking structure. Save that one for university, you're not going to spoil that one if you do chemistry. Now when we go on to what we're actually here to do, so what these are just reminding you what some other examples of empirical formula. Combustion analysis. Combustion analysis is exactly what it says. You take the substance and you burn it. Now you don't literally burn it and just, oh, it's gone. That's not right. What you have to do is you have to trap the product. So if your compound is not combustible, you can't do combustion analysis. But that does mean that if you did combustion analysis of organics like this, it would work, they would burn. And you would get carbon dioxide. You find out how much carbon dioxide in terms of mass there is. There's a little diagram of how you trap carbon dioxide and water. It's not actually how it's done really. It's done in a machine these days. You put the stuff in, does it, gets the result, prints out. But there's a sort of schematic of how you do it, where you trap the carbon dioxide in one way and then you go and trap the water in something that absorbs the water. So most combustion analysis is based around carbon dioxide and water collection. Now if you burned ethene, you would get, and it's full access to oxygen, complete combustion, you don't want any carbon monoxide or any particulate carbon. So that would produce CO2 and H2O. Here this would still produce CO2 and H2O, it's just that some of the oxygen is in the structure. If you come outside that and you have something perhaps with nitrogen in the structure, which you do get at A level, you get amines and amines, when you burn those, you get, apart from CO2 and H2O, you get nitrogen, you get N2. It's not high enough temperature to produce nitrogen oxides. So you get N2, so you get an example of N2. If you did this with a halogen, you might get the Cl2 or Br2 come out, and you would have the mass of those collected and given to you in the question. So that's the setup. What you get is you get a set of results. You get a set of results. How many grams of carbon dioxide? How many grams of water? Usually that's it. We'll go through how you do it in just a second. Sometimes you get a mass of other things as well. And you go from the number of grams of those given products through to an empirical formula. Empirical formula doesn't tell you the actual formula, you get extra information that is usually off, well, most of the time that's in the form of a bit of mass spectrometry data, of which the largest mass to charge peak, the one furthest up the scale, tells you the formula mass, and if you look at that and you go, oh, that's the empirical formula is do that 3 times, you can then turn the empirical formula into the molecular formula. We're going to do some examples. There's only 2 because it's really straightforward, and I'll see you shortly. So here's first example, and the object has appeared because the camera operator is eating it, but it's here now. First example of a combustion analysis. So here's the question. Well, most of the question I just rubbed out the G. Complete combustion of a 2.560 gram sample of a hydrocarbon produced, and here's the amounts of CO2 and the amounts of H2O, 7.822 grams of carbon dioxide and 3.840 grams of water. This piece of information, it's kind of not required, it's spurious to this question, but it's in there because there's a little check you can do. But also, when we do the second example, the mass of the actual sample is important. So these things are often worded like that, whether you need the mass of the sample or not in answering the question. So there's the question up to there. Put a line. So there's the question. Now, the process for this, now this is because it is a hydrocarbon. So because it's a hydrocarbon, we don't have to consider any other elements. We don't have another column for oxygen, which is the most common additional thing. And it's the oxygen we're going to be doing the second example. So what you do, it's the standard thing. You do it the same every time, and it even picks up from the percentage by mass analysis halfway through. So the first thing you do is you take the mass of carbon dioxide and you determine, from a simple little calculation, how much of that mass of carbon dioxide is actually carbon. So you take the mass of carbon dioxide, and 12 out of 44, formula mass of carbon dioxide, always worth remembering, is 44, carbon is 12, so 12 out of 44, 12 grams out of 44 is carbon, multiplied by the mass of carbon dioxide, and out of that comes the number of grams of carbon, which is there, 2.1333. Now you look at the number of decimal places, you think, oh, that's way too many. The point is, you go over on the number of decimal places just to make sure you don't round something too much and come out with a ratio that it doesn't quite work later on. So I would always go like 4 or even 5 decimal places, because you get rid of it at the end anyway. So 7.822, 12 lots of out of the 44, and you multiply that, you get number of grams of carbon. Doing the water, in the formula of water, 2 grams out of the 18, or 2 out of 18, are hydrogen in the formula of water. Now, I've always taught this with 2 out of 18. A couple of years ago, 3 years ago maybe now, a girl who I very rarely name check anybody in this, Emma, said, you don't need to do 2 divided by 18, you just divide by 9. And I said, if you want to do that, gives you the right answer, do it. So I either do 2 divided by 18, multiplied by the mass, or just go divide by 9. I must be honest, I go with divide by 9 because it seemed like a simpler way to do it. But that's the real reason. It's 2 out of the 18 for the formula mass of water, and that comes out as 0.4267 grams of hydrogen. So there's a lot more carbon than there is hydrogen in terms of mass, but it's not about that. It's not about the mass, it's about the number of moles. So you've got to convert it into number of moles. You divide by the formula, not the formula, the atomic mass of the element. So carbon gets divided by 12, and we get 0.1778. That actually is the number of moles, but I'm not putting a unit on because it doesn't really matter. 0.1778, and divide that. Oh, hydrogen is 1, so it doesn't change the number. So the numbers we're working with, 0.1778 and 0.4267. This is where it overlaps with the percentage mass analysis. You then go, let's divide by the smallest. And the smallest out of those two is this one. So that divided by that is 1.0. That divided by the 0.1778 is 2.4. So 1 to 2.4 is a ratio. Empirical formula have to be whole numbers. You did remember that, didn't you? And so the easiest way to do that is just go, oh, I'm going to do multiples. Now there were 2 ways to do that. You can go, I multiply by 2, do I get whole numbers? I multiply by 3, do I get whole numbers? I multiply by 4, do I get whole numbers? It's only about this one because obviously that will be a whole number every time. And you end up with 5 and you get 2 whole numbers. Or you can just go, I multiply it by 10, which is what I've done this is the way I've done this one. Multiply it by 10, I get 10 and 24. So C10, H24, but 10 and 24, just like right at the beginning, they both divide by 2. So that makes the formula C5H12. So this is the reducing of an empirical formula that's not an empirical formula because it's not the lowest ratio, down to the lowest ratio, which is C5H12. That's pentane. Hydrocarbon analysis, straightforward. When you've got oxygen involved, a little bit more. We'll do that one as the second example. There's only 2 examples today. And then a load of questions that you can have a go at. Did you write this down? Do you think you should be pausing me and writing this down if this is brand new to you? Are you pausing me? I haven't stopped. See you in a moment for the next example. Second, last example for that matter, because there's only these 2 skills to know really. So here's the second question. Complete combustion of 3.675, just in case you can't read it. I realise it's you might be on a small screen. 3.675 grams sample of an organic compound containing carbon, hydrogen, and this time and oxygen. And it produced 7.350 grams of CO2, 3.007 grams of water. Analysis process is the same for carbon and hydrogen as it was in the first example, but we have to do something a little bit different to get the oxygen, because oxygen is within the compound and then there'll be oxygen coming in from the combustion using the atmosphere of oxygen. So we need to establish how much of the mass of the compound was oxygen within the formula, the structure. So, same thing as before, 7.350 times 12 of the 44, 2.005, divide that by 12, we get 0.1671. Same process for the hydrogen, 3.007, I've done the Emma, I've divided by 9, I shouldn't call it that, which is 0.334, divide by 1 for the hydrogen, 0.334. To get the oxygen, what you do is you take this mass here, 2.005, and this mass, 0.334. So you take the mass of carbon and the mass of hydrogen, and as the mass of the actual substance, 3.675, is only made up of a number of grams of carbon number of grams of hydrogen, number of grams of oxygen. If you take the 3.675 and then subtract from it the mass of carbon and the mass of hydrogen, what's left was the mass of oxygen. It looks quite large, but then oxygen is a heavier atom than either carbon or hydrogen, so it does that kind of thing. And then you take that number of grams, that's a number of grams there, put G on the end, there it is, put G on the end. Divide that by, this time by 16 because it's oxygen, and we get 0.0835. And then you do the same thing as before, you divide by the smallest. Now in this case, the smallest is 0.0835. So 0.0835 is 1 for the oxygen. You do that, you get 4, you do that, you get 2. That's come out nicely, come out wonderfully, because 2, 4 and 1 already integer values, whole values. So that makes the empirical formula C2H40, oxygen, C2H4O. Now I've kind of took it a little stage further and said, does this, what I'm thinking is, does this compound, CH3, CO2, CH2, CH3, which is ethyl ethanoate, does it match this analysis? Well, you need to convert that, you need to condense this structural formula, as that is, down into a molecular form, which is C4H8O2. Does that match that in terms of empirical formula? Well, yeah, that doubled is C4H8O2. So that empirical formula could be, I'm not saying there aren't other things, I haven't thought about it, so, but it does fit with the empirical formula we've got. So this question could have been, show that this analysis is consistent with the formula of, in this case, so this one here, CH3, there. That's kind of it. So there are only two things. There is it's a hydrocarbon, we don't have to consider oxygen within a structure, and then there's oxygen within a structure. Taking it a little stage further, you do have, sometimes you get, oh, there's an additional element. And there's a couple of questions where you've got that, but if you give them a go, you'll see how you get on. So there is an accompanying set of questions, ends with an exam style question, and worth having a practice. And yeah, that's kind of it really. Give yourself a go with the practice questions. Answers are there as well. And, well, it's been nice seeing you. If you want lots more examples of analysis, I've got a book coming out, I said that last time. Been working on it this morning, still not quite finished. But, I'll see you for the next video very soon. Thank you very much. Bye.